Hello, everyone, and thank you for joining us for Inspectioneering's latest webinar, Understanding the CCD IOW Implementation Process, brought to you by E2G, the Equity Engineering Group. My name is Jeremiah Wooten, and with us today is Brian Jack, Principal Engineer 2 at E2G. Brian has been involved with materials and corrosion issues in the refining and chemical processing industries since the early 80s. His 35-year pre-E2G career was split between Chevron and Phillips 66, where he was exposed to a good mix of in-plant and corporate assignments, enabling a highly experienced and practical approach to solving materials and corrosion problems. Prior to joining E2G in 2016, Mr. Jack served as the Chief Materials and Corrosion Engineer for the Phillips 66 refining system, which included 14 refineries worldwide. In this role, he led system-wide mechanical integrity improvement efforts, trained numerous inspectors and engineers, and helped solve a wide array of refinery corrosion and metallurgy problems. Over the last 35 years, Mr. Jack has also served as a working member and in lead roles with industry standards organizations such as API and NACE International, now known as the Association for Materials Protection and Performance, or AMPP. Brian, thanks for joining us and for leading today's presentation. Now, before we begin, a few housekeeping notes. First, all attendees' microphones and videos have been disabled today. However, we do want to hear from our audience members. So if you have any questions for Brian, feel free to submit them at any point in the Q&A box located at the bottom of your Zoom window. Next, we know how busy everyone is and want to be respectful of your time. This webinar is scheduled for 1 hour, and we will do our best to get to all of your questions in the allotted time frame. Any questions we are unable to get to will be addressed by a member of our team after the webinar. Finally, this webinar is being recorded and a replay will be made available to all registrants within 1 week on inspectioneering.com. So if you enjoyed today's presentation, please do us a favor and share the replay with anyone you feel would find it helpful. Now that that's out of the way, I'd like to go ahead and turn things over to Brian.
Okay, thank you very much for that intro, and good morning, good afternoon, or maybe even good evening, depending on where you are. I'm going to jump into this PowerPoint presentation. So this presentation covers CCD IOW implementation processes. This is a similar version to a presentation I gave several years ago at the API Inspection Summit, but with a few enhancements. You've already got the introduction on my background, and just to add a little bit more to that, my experience, although I do have some experience in chemical plants and upstream, my primary experience has been with refining my entire career. Okay, first part of this presentation, I want to talk about integrity operating windows. That's a term that is also, that is the most common term used in industry for this concept, but some refineries use other terms like refinery operating limits or materials operating envelopes. They all covering the same things. Anyway, regarding IOWs, analyses of industry fixed equipment failures have identified that a key root cause for many refinery failures is prolonged operation outside of recommended ranges, and that in-service inspection programs, even when they're fully code compliant and thorough, cannot be counted on alone to prevent incidents. Most of you familiar with the API inspection requirements know that most equipment in refineries is inspected at 5 or 10-year intervals, depending on their API classifications. There's a few critical equipment areas like injection points that are inspected on a shorter interval of 3 years. But those intervals are just not frequent enough to prevent incidents with out-of-control operations. Corrosion rates are too high, and intervals of 5 or 10 years are just too long to catch rapid corrosion damage before a leak or incident will occur. So the conclusion from these analyses of many industry failures is that excellence in operations, which is ensured through IOW programs, is required to achieve high levels of fixed equipment mechanical integrity. Here are a couple example failures, real-life examples of refinery failures due to poor operational control. And these failures were certainly not preventable via inspection programs. And you can see that by the corrosion rates that we show in the center of this table here. I'd like to touch on these three incidents, and there are many, many more, but I do have some personal experience with these three and give you a little more background. First one is a crude unit overhead, and it was an amine chloride salt corrosion failure and a exchanger bundle. In fact, the first bundle was replaced. Good failure analysis was not done. A new bundle was installed and failed in just 18 days. Now, those of you refiners that run fracked crudes might be familiar with a unique problem that the industry has with fracked crudes, and that is tramp amines or H2S scavengers coming in with the crude. And when that happens, those tramp amines, those H2S scavengers, can form amine chloride salts in the crude unit overhead. And as far as an IOW, often the first inclination that you got that problem going on is a high pH value in the overhead waters. Typical control range for crude unit overhead waters using neutralizing amine inhibitors is 5.5 to 6.5 pH. That's ideal. In this particular case, they were measuring pH as they should have been routinely, but they were seeing pHs above 7.5, above 8. Unfortunately, the refinery was not aware of the implications of that. To some more knowledgeable folks, that would be a clear indication that you'd have this amine chloride problem, salting problem occurring in the overhead. But this particular refinery didn't seem to appreciate or acknowledge the high pH as an indicator of some significant trouble coming. So that was some awareness of unawareness of the IOW control range in that refinery. This second example, this FCC unit erosion of a slurry piping system, IOW involved there is the ash content at the bottom of the FCC fractionator. That is a common IOW in most refineries, and a common limit for that ash content is 0.5 weight%. If you have ash content higher than that, it indicates a lot of catalyst carryover from the FCC reactor to the fractionator. The result of that catalyst carryover can be erosion failures, particularly in the high velocity slurry pump area at the bottom of the fractionator. And that's in fact what happened here. This is another case where the refinery was measuring that IOW routinely, but that IOW was not being communicated really to anybody outside the unit process engineer, happened to be a young person, and probably did not appreciate the erosion problem that catalyst carryover could promote. Certainly aware that he had problems with his cyclones, and they were going to address that at an upcoming turnaround. But the fact that the ash content was so high was not being communicated to other people in the organization, such as inspectors, who could have taken some action, started looking at that bottoms piping around the pumps, and prevented a failure, which did cause a fire in this particular case. And then this third example is an HCl ammonium chloride failure at a mix point, where a reformer overhead stream containing dry HCl met up with a wet stream in a HDS unit, stripper overhead. And as many of you on this webinar know, when you mix moisture with HCl, dry HCl, you form hydrochloric acid, which can be extremely corrosive. This is a case where a routine IOW was not in place to check the chloride content of the stream leaving the reformer overhead. And they did have a chloride guard in that reformer overhead, but the absorbent was spent. And in fact, they had done some bypassing of that chloride guard bed in the months prior to this failure. So that last case is a case where an IOW that should have been in place and shared with the organization, that just was not occurring, and it led to a failure. A significant release of LPG, but fortunately, no significant event resulted as that LPG cloud did not light off. There are many, many more examples like this, where out of control operations and not implementing IOWs properly or not at all led to rapid corrosion failures that were not foreseen by the location, but probably should have been. So 5 key elements to mechanical integrity, and the one we are focused on today is excellence in operations and the fact that IOWs are key to excellence in operations. There are many other good key elements. There are many other key elements to mechanical integrity: good design, quality construction, excellence in maintenance, and excellent inspection that all play into it and have very, very important roles in mechanical integrity. But today's focus is on excellence in operations and the fact that IOWs are key to that in terms of obtaining a high level of mechanical integrity in a refinery. Document API RP 584 was issued in recent years to acknowledge the importance of IOWs in ensuring mechanical integrity in refineries. So what are the key goals of an IOW program? I really like the first bullet on the left here, that definition. IOWs ensure good communication. That is really the key function of IOWs, and I'm going to emphasize that point several times in this presentation. So IOWs ensure good communication of equipment limits and exceedances between key process operations and MI personnel such that equipment can be safely managed and operated without loss of containment or unplanned shutdowns between scheduled turnarounds. So that's a bit of a mouthful, but bottom line is use IOWs to get your problem solvers, troubleshooters in a refinery, proactively working problems so that you don't have loss of containment or unplanned shutdowns. Another key point about IOWs is they are meant to ensure that IOW limits are intended to result in predictable and reasonably low rates of equipment degradation, not zero. There is going to always be some equipment degradation that inspection groups need to stay on top of. So our goal of zero degradation is unrealistic in modern refineries. Over on the right, there's a chart that shows the concepts of IOW limits, and some important things to point out here. There's often a target or optimal range, and let me go back to that crude to overhead pH example to maybe illustrate this. So in many crude unit overheads, again using neutralizing amines for overhead neutralization, have a optimal pH range of 5.5 to 6.5. And that's where we'd like to operate, of course. It's not unusual to have some excursions above or below those ranges. And how aggressively we need to react to those excursions depends on how big they are. So, for instance, a low side pH of 5.4 is probably not going to cause a lot of consternation to people looking at that data. It's good to get that information out that we had some low pH readings below 5.5 to, again, the key personnel, so they could take some long-term proactive actions to get pH back in the target range. Maybe they need to inject more inhibitor in the overhead to do that, or neutralizing amine inhibitor to achieve that goal. Need some larger diameter tubing or piping. Could be something like that. At a lower level of pH, say 4.5, we probably want a heightened sensitivity to something like that, because failure will occur for sure with sustained operations if we have pHs below 4.5 and a crude unit overhead. So we want more aggressive action on that. If we get to a critically low or high pH, say on the low side 3.5, failures could occur quickly, and we certainly want the whole organization engaged in a rapid solution to a problem like that. So that's what that chart on the right is showing about IOWs. Now, with some IOWs, they don't necessarily have a target range. They might just have a high limit, like tube skins on a heater tube. But the same concept applies. You probably want some conservative limit on the high side that will ensure long furnace tube life, and then as tube skid temperatures get hotter and hotter on those furnace tubes, you want a higher level of engagement and a quicker response time to the issue to prevent a failure. So continuing on with the IOW program key goals. Once again, don't view IOWs as a hard not to exceed limit. There is some flexibility there, particularly when we assign somewhat conservative target ranges, which we should do. But do, again, view them more as a communication tool. That's really the key goal here. And at minimum, IOW exceedances should force a communication between your process engineers, your mechanical integrity subject matter experts, such as lead inspectors, corrosion engineers, and operations supervision to determine the best corrective action. That's what we want to do. We want to get those people together to determine the best corrective action through an IOW exceedance. Historically, in refineries, from my experience, especially going back many years, a lot of these experts, process engineers, and then the mechanical integrity people and the operations folks, can tend to work in their own silos. They're doing their jobs well within their area of specialty, but to be really good at ensuring we don't have mechanical integrity events in refineries, we need that communication, and that's what really IOWs do, forcing those communications between these key people in the refinery. So typical responses to IOW exceedances can include immediate operations adjustments to restore the IOW to the target range. That is the generally preferred action that we like to see, but sometimes that's not practical or readily achievable, or maybe just not economic for the refinery. Another typical response could be adjustments to the inspection plans of those areas suspected of experiencing accelerated damage. And that's a really good notion that has come a long way in recent years. Again, if you look at inspection departments historically, they tended to follow those API code intervals for inspection of 5 or 10 years or 3 years for injection points, and operate in a silo with that information, only adjusting those plans if their data indicates they should, but not taking into account operational changes that are occurring in the unit. And that's how we get surprised. Another response could include initiation of projects to address the exceedance if it's not easily correctable via operations adjustments. So maybe we need a new water wash, maybe we need some new chemical inhibition, some alloy upgrades, a new larger separator, all those types of things. It's always good to plan, be able to pre-plan those type of changes versus having a failure and then realizing you need to make those kind of changes on an expedited basis. So by having IOWs in place, it gives us much better opportunity to do pre-planning for those types of projects that will help manage our mechanical integrity over the long haul. And then finally, we could have another response could be installation of some preventative clamps, temporary repairs, to ensure a leak and LPO-free run until the next scheduled turnaround. So, and we can have a combination. It could be a combination of responses. One example I was involved with not too many years ago was a crude unit overhead again, and we had a pretty substantial reduction in the tower overhead temperature. That was economically advantageous to the refinery to make that adjustment, significantly economically advantageous. But some of the fixed equipment and corrosion engineers at the site were concerned that by lowering that tower overhead temperature to below an established IOW would lead to chloride salting and corrosion in the overhead piping, which was just carbon steel at the time. So the plan was made that they would lower the temperature, inspection would accelerate and frequently inspect that overhead piping. Some permanent scaffolding was established to enable routine, frequent inspections. That was all planned, and sure enough, the inspectors started identifying salting and corrosion damage, and became concerned that, hey, we're not going to make it to the turnaround without a leak and an unplanned shutdown. So a project was initiated to purchase some alloy piping that would go in at the turnaround and to install a new water wash. But several temporary cocoons were established over some segments of the overhead piping that were showing the most corrosion and salting. So multiple responses to an IOW exceedance, which in this case was a lower than desired crude unit top temperature. But communication was good, plans were put in place, projects were initiated, inspection was activated, and got to the turnaround without any leaks or unplanned shutdowns, and then installed the alloy piping and water wash, and the problem was taken care of. Okay, so IOWs are typically developed when refineries begin an IOW project. They will develop IOWs for all the major units in the refinery. And it's typical to document these IOWs in tables that are easy to read and provide a good source of knowledge for lots of people in the plant: the operations folks, process engineers, inspectors, and corrosion engineers. A typical IOW table for a refinery unit would provide the following information. So the list of recommended IOWs, the test or sample location for the IOW, along with PI tag numbers were available. PI tag numbers become important for IOWs as they are used in notification tools. Recommended limits, often a max, min, and ideal target range for the IOW, as we described earlier. A recommended sampling frequency for the IOW, is it daily, monthly, yearly? How continuous, how frequent are we going to sample? The recommended API 584 IOW type. 584 recommends basically 3 categories of IOWs: a critical, standard, and informational. You might look at those as a prioritization of the IOWs for the unit. The possible consequences of IOW exceedances and deviations. I think this is a really important part of the IOW table because it provides that knowledge base. So what's going to happen? Like that young FCC process engineer I talked about, that when he was having the catalyst carryover into the fractionator, was not well apprised of the possibility that could lead to rapid erosion damage in that fractionator bottoms piping. But if it's documented on these IOW tables, he's got that information in there. What are the consequences of that IOW deviation? And it's captured knowledge for all future people coming into the refinery. The corrosion loop or loops impacted by the IOW. Some refineries, instead of using the term loop, use corrosion systems. But it's good to know if we got an IOW exceedance, what parts of the unit do I need to worry about the most? That's valuable information for inspectors, for instance. Some recommended operations process responses to IOW deviations. It's pretty much impossible to cover all the possible responses, but you can cover the typical or most common responses in this IOW table, and that's what should be done. And similar for their recommended inspection or mechanical integrity subject matter expert responses to IOW deviations. What are some exceptions or clarifications to IOWs? What do they cover and not cover? IOWs do not address design limits for equipment, pressure and temperature limits. It's an interesting point, but most failures in refineries are not because we exceeded design pressure or design temperature. Our construction codes for refinery equipment are quite conservative with their safety factors, and it's pretty rare that we fail equipment by exceeding pressure and temperature design limits. It is much, much more common that we fail equipment because that's degraded in some way. It's corroded. It's developed cracking, that sort of thing. IOWs, to this date, tend to cover fixed equipment only, not rotating equipment, instrumentation, or electrical hardware. They are typically excluded. There are some changes I'm seeing in some refineries starting to implement IOWs in those other discipline areas, but fixed equipment only is typical. Why? Fixed equipment accounts for most LPO and significant mechanical integrity events. Fixed equipment failures account for most of the significant LPO and significant safety-related mechanical integrity events in refineries. IOWs do not address product quality or product specification limits. Those are covered by other systems. Also, for damage mechanisms that can occur or are strongly influenced by short duration upsets, they are not really capable of being controlled by IOW limits. And some examples of that are like brittle fractures of equipment during unit startups or during a hydro test due to not adhering to a minimum pressurization temperature. That type of damage or event just happens too quickly to be covered by an IOW, where alerts go out to various subject matter experts and engineers and inspectors and so forth. You don't really have time to discuss that. You just need to have those hard limits in place on an NPT to avoid a brittle fracture. Another example is fatigue failures of inadequately supported small bore piping near pumps or compressors due to excessive vibrations. A couple cracking examples: polyethylene cracking or chloride cracking of stainless steels due to either, in the case of polyethylene cracking, not applying or misapplying soda ash solution, or in the case of chloride cracking, not thoroughly draining and drying your stainless equipment prior to unit startups. And if you boil dry that chloride containing water in a stainless piping system, you're very likely to crack it. So those kind of cracking problems need to be covered by operational procedures that need to be handled well during turnarounds. There's really not much of a place of IOWs in preventing those kind of instances. So it's not, IOWs can't cover all forms of failure and damage prevention in refineries, but they can cover quite a few of them, the bulk of them. More clarifications on IOWs. The appropriate specific timing for operations, process, and inspection responses to an IOW exceedance is kind of beyond the scope of an IOW table. You just got to get the smart people in the refinery involved. Let me give a good example of this issue again on that crude unit overhead pH. We talked about a typical target range of 5.5 to 6.5, but we talked about a pH of 5.4, a little on the low side, not being that big a deal. Really don't need to jump through a bunch of hoops for a response on that. But certainly, if you get down to a pH of 4.5 or even worse, 3.5, you're gonna want a rapid response on that. And most IOWs are like that. It's okay, an exceedance. We definitely want to communicate all exceedances, even the minor ones, to key people. But as far as response time, that depends on the magnitude and duration of the exceedance, and you need subject matter expert knowledge to provide the input on the proper timing. and it can be complicated. And then finally, IOWs for process units typically do exclude the unit's utility systems, although you should have IOWs for your utility systems eventually. It is assumed that IOWs for these systems are usually covered in the utilities units themselves, and that's how most refineries do handle that as well. How many IOWs? You'll get some debate in industry on this. I'm a believer in trying to keep it as simple as possible and quite targeted. So from my experience, typical is 10 to 25 IOWs per unit, with some ranges from 5 to 40 IOWs per unit. Examples of a refinery unit where you probably see a high side of IOWs is an HF alkylation unit. That's not uncommon to see 40 or maybe even more IOWs in a unit like that, where there's lots of important IOWs that are critical to keeping corrosion rates manageable on the alloys used in an HF unit, mostly carbon steel, but some Monel as well. On the other hand, smaller units like sour water strippers might just have a handful of IOWs, 5 or 6. And that's probably sufficient for units like that in most cases. I always advise to target those variables or IOWs most likely to cause equipment failures based on industry experience. We've got a lot of experience in refineries as to what causes failures and what IOW exceedances were typically behind those. So focus on those. Don't get lost in the weeds considering every possible variable that can promote some equipment damage. Minimize redundancy in establishing IOWs. If the temperature limit alone will provide high temperature hydrogen attack protection, then you don't also need a hydrogen partial pressure limit. So minimize redundancy. I've already mentioned this. Fixed equipment failures cause the most LPO and most serious safety-related incidences in refineries. So limit IOWs to fixed equipment only, at least to start. Don't overwhelm your people or systems. It's better to start small. I think refineries that have implemented some of these IOW programs, in some cases, they put together IOWs for all their refinery units and then got their PI tags information into their notification systems. Then they hit the go button and the people who get notified on exceedances get overwhelmed with the data to start sometimes. So there's often some adjustments needed to the actual IOW ranges. I also believe it's beneficial that depending on the magnitude of the exceedance, you don't necessarily need to notify everybody in the refinery about a pH excursion and a crude unit overhead of 5.4, below the lower limit of 5.5. In that case, maybe just notify a few people, your refinery corrosion materials engineer and maybe the unit engineer of that small exceedance. They could probably take the issue from there. A much bigger pH excursion, then you probably want to expand the amount of people being notified. So that's the gist behind the comment of do not overwhelm people and systems, and better to start small with these IOW programs to help ensure the success of the program. So what does good look like for a refinery IOW program? I've seen IOWs implemented in many different ways at refineries, and I do think there's a lot of ways to skin the cat, but here are some common things I see in programs that seem to function pretty well. One, there's a RLT, refinery leadership team level, site owner established. Maybe it could be a tech manager is a pretty common one I've seen. Sometimes it could be the operations manager. But you want some high level management ownership for these programs. You have IOW tables developed for each major refinery unit containing the info I showed on that previous slide as a minimum. You want very few IOWs alarmed, just a few critical. I don't think you need to set yourself up for a lot of alarm overload with these programs, but you do want timely electronic notifications provided to your key personnel. Again, this can and probably should be a very small group of key personnel for minor exceedances, expanding to maybe additional personnel when the exceedance is fairly dramatic and needs some more rushed action to correct. Stewardship meetings, that's another key aspect of a successful program that I've seen. Stewardship meetings that involve this site RLT level owner and the other key SMEs involved in the IOW program. Meetings are not popular in refineries. There's too many of them. They're too long. So I've seen these meetings conducted, and the efficient ones, you have that tech manager, that RLT level owner, just say, hey, look, where are my IOW problems? Which ones are the greatest risk, and what action plans do I have in place to address those? So focus on the key items. I don't think you need to get people together to go through reams and reams of data and trends and charts and so forth. But efficient meetings identify the key risks, and efficient managers make sure that they got action plans to address those key risks. And another key aspect of a good IOW program is that they're revalidated every 5 years maximum. And I think it's good to tie these with the unit PHAs. It's a good package to review with your PHAs and helps make your PHAs more effective. Their IOWs often need tweaking from the initial program that is put together. That's very common in refineries. So you want to get the right people together to review what makes sense, make proper adjustments. So to summarize IOW programs before we move on to CCDs, IOW programs are a tool to ensure that the refinery's key troubleshooters, again, process engineers, mechanical integrity SMEs, operations supervision, are communicating. Again, that's the big emphasis here. You want those key troubleshooters communicating, not operating in silos, and proactively working on issues that could jeopardize the refinery's reliability and profitability. IOW programs are essential to ensuring high-level MI in a modern refinery. They are a time-proven and valuable tool for reducing process leaks and LPO. And data has demonstrated that in refineries. They do better in these regards when they implement a good IOW program. IOW should be a precursor to developing site RBI programs. That's really not how it's worked in industry, but they should be. So if you haven't developed your RBI programs, I would put together an IOW program first. And IOW should be an integral part of inspection planning, which, again, was not historically the case. Again, inspection planning tended to focus around API inspection intervals without properly taking into account how operations are changing in their refinery unit. And refineries are much less steady state operating plants than they were historically. Much more variation in crude slates occurs, and much more debottlenecking in refineries. So lots of changes in the refining industry have made this more important than it was even historically. Okay, so that's key background on IOWs. And now I want to move on to corrosion control documents, CCDs. That's the abbreviation for that. So a question that I've seen many high-level refinery managers ask, and it's a good one. So why do we keep experiencing significant failures from damage mechanisms that have been known for decades? We have a pretty darn good understanding of most of the damage mechanisms in refineries, but we still keep having failures from those same old damage mechanisms. And the short answer that I have for that is that the plant people who need to know about these damage mechanisms, how to avoid, control, and inspect for them, have not had the adequate training and knowledge transfer required to fully understand lessons learned in the past. And who are some of these key plant people who need to know? Well, inspectors, corrosion materials engineers, process unit engineers, fixed equipment engineers, and the managers and supervisors of all the above. That's a key core of people that I think need to have some basic fundamental knowledge about damage mechanisms and how to avoid, control, and inspect for them. CCD development, the refining industry. So the key goal of the CCD is to take the generic damage mechanism information available in resources such as API 571 and provide a damage mechanism document that is very specific to the process chemistry, metallurgy, and design of a particular unit. IOWs are or should be a subset and integral part of a well-done CCD. It is my strong belief, and a lot of refineries that implement CCD programs do it in conjunction with development of IOWs. I think it's a good package to be done together. They're very interrelated. CCDs should be developed as forerunners to RBI, and CCDs should cover all fixed equipment in a unit, not just vessels. I think those of you familiar with RBI know that in the early years, certainly RBI was focused almost exclusively on vessels. Has expanded in recent years to cover other key items of fixed equipment, but that has not occurred in all refineries. But CCDs should for sure cover all fixed equipment in the unit, piping, exchanger bundles, anything that can lead to anything where failure can lead to LPO and or loss of containment. Like IOWs, API has developed a document, RP 970, to recognize the importance of CCDs in refinery MI programs. CCD document came after the IOW document, was approved in 2017. And many refineries are developing unit-specific CCDs for each of the units in their refinery. To start a CCD project, the typical minimum required inputs are accurate, up-to-date PFDs, the metallurgy for all equipment, piping, heaters, and exchanger bundles in the unit, heat treatment condition of all vessels and exchangers and piping, recent key process data, turnaround dates and desired turnaround intervals, some inspection history highlights, and a list of recent and planned significant equipment and piping upgrades or replacements. Those are the typical required minimum inputs that I found necessary to get started on a CCD project with your subject matter expert. Typical deliverables from a CCD project are corrosion loop, damage mechanism, and metallurgy drawings, usually provided in PDF and CAD versions. Corrosion loop tables, again, on this loop term, some refineries prefer the term system to loop, but loop and system are the two most common terms used. And anyway, loop tables provided typically in an Excel workbook with the following information provided for each loop. A loop description, the primary corrodants and normal operating conditions in the loop, the materials of construction and comments on material suitability and areas of vulnerability, a list of loop damage mechanisms. So this is really important part of the CCD. What are the damage mechanisms we're worried about most in the loop? For the subject matter doing the CCD, what is the assessment of the risk of that damage occurring? And what are the effective operational and inspection mitigations for preventing damage and failure? in that particular loop. So that's a very key part of the CCD right there. Key IOWs should be listed, what key IOWs pertain to the loop in question, and key issues and concerns. So after reviewing all this information on the loop, what are the key recommended actions going forward on that particular loop? I think all this will become a little clearer on this example I'm about to provide here. Okay, so I mentioned that CCDs will have these loop drawings or system drawings that break portions of the refinery unit into areas where common forms of damage are likely to be present in the loop. And fairly common operating or process conditions exist in the loop. There are many different ways and interpretations on how best to break loops and systems. It's perhaps not all that important as long as you've got the damage mechanisms well covered and recommendations around inspection and operational controls to minimize or control damage to the best extent possible. So this example here I'm showing is a segment of a hydrotreater reactor effluent air cooler system. So this is the reactor effluent of a hydrotreater. I think that many of you folks experienced in refining know that REAC systems, as they're often called, are a common area of industry failure and problems historically because of some aggressive corrosion mechanisms that can exist in this reactor effluent air cooler loop, such as ammonium bisulfite corrosion and ammonium chloride corrosion. So we'll show some more details on this loop CL2C on the next slide. But let me point out a few other things that make these CCD drawings pretty handy. You can see that all the metallurgy for the exchangers and vessels and piping are provided on the diagram. Over here, upstream of the REAC proper, there are some 5 chrome piping segments. Moving into the exchanger, we have a chrome bundle and a chrome channel, but a carbon steel shell. All those have been heat treated. That's what all those symbols on the exchanger there. The circle represents the shell metallurgy and heat treatment. The rectangle represents the channel side metallurgy and heat treatment, and the diamond represents the bundle metallurgy. Over on the cold separator up here, we can see it's a post-weld heat treated carbon steel cold separator. The REAC itself is constructed of carbon steel. Basically, this REAC system is an all carbon steel system. At the bottom of this drawing, for each loop, there will be a list of the prevalent damage mechanisms or the damage mechanisms of greatest concern for that loop. These little circle numbers 83 are some key injection mix points in this particular segment of this CCD drawing. So the refinery knows that these have been identified by a subject matter expert as key injection mix points and required even more frequent and thorough inspections than other portions of the loop. So I think maybe that's enough on the introduction of what a CMD drawing can look like. Again, there are many different options to represent this, but yeah, you want your loops identified, you want your metallurgy identified, you want your damage mechanisms listed at the bottom of the drawing. But then again, for each of these loops, they should be accompanied by some more detailed information. I know this slide's real busy. We're not going to read everything on this slide, but this is an example of a write-up on the previous slide, that loop CL2C, that REAC system. This is the write-up on that loop. And key things that I like to see in the CCD loop write-up, of course, are the loop identification, the primary corrosive concerns, the operating conditions, what are the materials construction, some comments on material suitability. You can see in this case that We are a little concerned about the long-term viability of carbon steel throughout this system based on the damage mechanisms present, their history they've had, and some of the process variables that were reviewed. And then in this middle section of the table is a listing of the key damage mechanisms of concern and a qualitative assessment of the risk of that damage occurring. So you can see that this loop has medium-high risk of ammonium bisulfite, ammonium chloride, injection point, and wet H2S damage. And in fact, their history has shown that this to be true. And we have some recommended in the far right portion here of the middle section of this table. We have some effective mitigations recommended, both operational and inspection-wise. Towards the bottom of the table, we have some key IOWs listed and some recent readings for those IOWs. At the very bottom of the table, we have highlighted our key issues and concerns. In the body of the CCD report, we provide some recommendations on these key areas of concern for a unit. So anyway, again, many different ways to put together a loop or system table, but these are the key elements that you'd like to see in that. And this is an excellent, the drawing along with this table provide an excellent transfer of knowledge to new people coming into new roles as inspectors, unit engineers, corrosion engineers, inspection supervisors, operations supervisors. There's a lot of transfer of knowledge that can be well documented in the CCD, and that's key. You don't want to lose this type of information. So like with IOW, some exceptions or clarifications to what CCDs do or don't do. They cover the primary and most common damage mechanisms anticipated based on extensive industry experience. So you do want experienced SMEs, whether they're in-house SMEs or external, leading your CCD development, because you want that level of experience, and you want to make sure people you use for this have good knowledge of what the primary and most common damage mechanisms are, what the biggest risks are going to be for each particular loop in a refinery unit. Again, we don't want a list of every conceivable damage mechanism, just those most likely to cause problems. You don't necessarily need to go down the rabbit holes on theoretical damage mechanisms. By doing that, you ensure resources are focused on the primary or common damage mechanisms. External corrosion, big problem in refineries, but they are typically CUI and other forms of external corrosion like contact point corrosion, corrosion of pipe dummy legs, soil air interfaces, are not typically included in a CCD. Those types of external damage mechanisms are pervasive throughout refineries, basically everywhere when temperatures are less than 350. And usually there are site-wide programs to address that. That should be acknowledged in the CCD, and they're typically not covered in a CCD project. The injection mix points selected are based on PFD level reviews only. This is more when you have external resources assisting you with this. And another level, at some point, you should go into a P&ID level review to make sure you got everything included. Boiler feed water and steam systems are not typically included in the corrosion loops. And the piping and equipment metallurgy reported by the site is assumed to be accurate and fully PMI'd and retro PMI'd. So you want a good handle prior to doing a CCD. You certainly want a good handle on knowing the metallurgy, accurately knowing the metallurgy in your plant. It'll be hard for an SME to identify key risk areas if he does not have the full story on what the metallurgy is in the unit. So how do CCDs and IOWs benefit your facility? I think we've covered this pretty well, but this slide is just trying to summarize some of the key points. As far as inspection planning, they give you good guidance on where to inspect, how to inspect, what type of damage to look for, and process triggers for changing inspection plans. For operations, it provides you knowledge on IOWs, what the limits are about, and action steps to take when operating outside those limits. Training, CCDs and IOWs are a good training tool for essentially all new engineers, operators, and inspectors. You'll have different levels of training depending on the personnel. As far as training, though, it provides understanding how process MOCs and IOWs impact damage mechanisms, understanding impacts when operating outside of IOW limits, and personal responsibility, establishing the concept that everyone in the refinery owns MI. So we should be communicating to make sure we're properly addressing our MI risks in the refinery. Comprehensive MI programs include CCDs, IOWs. As I mentioned before, I really think CCD, IOW projects should be, for refinery units, should be implemented as a package together, and RBI. And again, I think we've covered these concepts, but to actually be comprehensive, to be able to state that you have a comprehensive MI programs, you should be able to show that you have CCDs in place, IOWs in place, and a risk-based inspection in place. All three elements. And again, I keep emphasizing this, but mechanical integrity is everybody's job. The best inspectors that I've come across in the industry know their damage mechanisms and a bit about the process too. I know historically, going back to that hydroprocessing unit we talked about earlier, I have gone into refinery hydroprocessing units and seen similar TML, CML coverage on the stainless steel piping in a reactor loop that I see in the carbon steel piping in a REACT system. When you see something like that, I say that just doesn't make sense. There's really no damage mechanisms that are going to cause thinning of stainless steel in my reactor loop, but there certainly is a lot of history and a lot of damage mechanisms that apply to carbon steel REACT piping. So I know when I go into a refinery and there's a lot more coverage, a lot more rigor about the inspections of that carbon steel REACT system versus the stainless piping upstream near the reactors, I know that the inspectors have a good understanding of their damage mechanisms, and it applies to other units too. There are the critical areas they should be really looking at, and not just applying, I take UTs and every other elbow kind of general approach to all their inspections throughout the refinery. Know your damage mechanisms. The best corrosion materials engineers ensure good communication between inspectors and operations process folks. They are really I found the best go-between between the inspectors and ops process folks. And the best corrosion materials engineers are focused on failure prevention versus failure analysis. I always hate to go into a refinery and see that the corrosion materials engineers are spending most of their time on failure analysis. I'd much rather have them looking at IOWs, talking to process engineers, and talking to inspectors about maybe alternate inspection plans, and going back to process and seeing what we can do about adjusting some of these process variables that are promoting corrosion. That's proactive prevention of damage. And then the best unit process engineers know and understand the effects that unit changes can have on MI. They're not MI experts, they're not corrosion experts, they're not inspection experts, but they should have the basics to know that, okay, if I have a high ash content in the bottom of my FCC fractionator, that could mean erosion in the bottom of the fractionator, and I got to make sure I'm talking to mechanical integrity people about that. So MI is everybody's job. Thank you very much for your time, and I believe we can take some questions at this point.
Thanks, Brian, and thank you for sharing those examples and valuable context. And thanks to everyone for joining us for today's webinar. I hope the presentation was helpful for you. Unfortunately, we are out of time and won't be able to address any of the submitted questions, but we'll do our best to get back to everyone as quickly as we can. To all the viewers, be on the lookout for a follow-up survey to let us know what you thought about the webinar today. Your feedback is extremely important to us and will help us improve these moving forward. I'd also like to extend a big thank you to our friends at E2G for partnering with us to bring today's webinar to the inspectioneering community. They've got a brilliant group over there, and we're looking forward to working with them to produce many more of these webinars in the future. And with that, today's webinar has concluded. Thanks for watching and have a great day.